Hello. In this video, I'm going to be explaining problem 7 from the 2018 F equals ma contest A. In this problem, we have a car that has a maximum acceleration of a naught and a minimum acceleration of negative a naught, and it asks for the shortest possible time for the car to begin at rest and then arrive at rest at a point a distance d away. So, this problem basically has an intuitive solution, and pretty much the first thing that you would think of is basically the right way to go. You may think that the best way is just to accelerate at the maximum for the first half of the distance, and then decelerate at max. For the second half. And it turns out that this is actually the right answer. So, in the first half, I'm going to show what time this would result in, and then later in the video, I'll actually prove it. So first, let's see what this intuitive solution would give us for the time required. So what we can do is we can draw a velocity versus time graph. And so let's say this is our final time t, and what will happen is that at first we'll accelerate. So this is v. So let's just call this t naught, and then this is the t-axis. So at first we will accelerate with some constant acceleration a naught, and so the slope of this line is a naught. And then halfway through, or how about, let me call this capital T. This is T over 2. And then now it will start decelerating. And this line will have a slope of negative a naught. So this corresponds to accelerating as fast as possible at first, and then decelerating as fast as possible afterward. And then the total area of this will actually equal the distance covered in this will equal the displacement of the car. So we want this, so first let's compute the height. So we know that this has a slope of a naught, and it goes in time t over 2, which means that this height right here is a naught times t over 2. And so now the area of the triangle, which is our displacement, and we want that to be d, we will have d equals 1/2 times the base, which is t, times the height, which is a naught t over 2. And so we get d equals 1/4 a naught t squared, and just solving for t, we get 2 times the square root of d over a naught. And going back to our original options, we will see that E is the correct choice. Now, if you're satisfied with that, you can move on. And honestly, I believe that this is probably what the test makers expected you to do, to basically just guess what, or to intuitively reason what the optimal answer would be, and then just go for it without proving it. However, I want to actually prove it for the sake of completeness. So how will we prove something like this? That this solution of accelerating as fast as possible at first, and the decelerating second as fast as possible, is actually optimal. Well, here's what we can do. Let us, again, let's suppose that we cover, let's say we have a certain time interval t, where we, and once again we'll split it t over 2, and we know that here at, we'll once again draw a velocity versus time graph. So at t equals 0, or sorry, little t equals 0, we know that we are at position 0, And we know that we have velocity 0. And we know that here, at t equals capital T, we know that we once again have velocity 0. And so now what we can do is that we can use, and we'll say that we're at some position x of t. And so now what we can do is that we can use the fact that our acceleration is never greater than a naught, and never less than negative a naught, to then integrate that in order to produce some bounds on where we can be at certain times. So first, we know that v prime of t is less than or equal to a naught. And we know that v of 0 is equal to 0. And so it follows, so v of t minus v of 0, which remember is 0, is the integral from 0 to t of a of t, where a of t is just v prime of t dt, but that is less than or equal to a naught times t. And so we get that v of t is less than or equal to a naught t. And now, x of t is less than or equal to, it is equal to the integral from 0 to t of v of t dt. But we established that v of t is less than or equal to a naught t. And so that means it's less than or equal to 1/2 a naught t squared. And therefore it follows that x of capital T over 2, that's a capital T, sorry, less than or equal to 1/2 a naught capital T squared. Now we can do our same calculations on the other side. So we know that x of t minus x of t over 2, let's start with v. So v of t minus v of t over 2 is equal to the integral from t over 2 to t of a of t dt. But we know that a of t is greater than or equal to negative a naught. And so we know that v of t minus v of t over 2 is greater than or equal to negative a naught t over 2. And therefore, let me correct this. So I want to use a general time t. So now we want to look at the interval where t is greater than or equal to t over 2. So let me just erase this. Sorry about that. And we just call this like t prime or something. So what we get is that v of t, so negative v of t is greater than or equal to negative a naught times t, capital T minus little t. So v of t is less than or equal to a naught times big T minus little t. And now x of t is going to be the integral, x of capital T minus x of little t is equal to the integral from 0 to integral from little t to big T of v of t dt. That's going to be less than or equal to the integral from little t to big T of a naught times t minus little t dt. And so therefore, and that will be 1/2 a naught big T minus little t squared. And so what we end up getting is that x of t minus x of for 2 is less than or equal to 1/2 is equal to 1/8 a naught t squared. And if you look at before, right here, so I realize that I made a typo here. That's 1/2 a naught t over 2 the whole thing squared, so that's 1/8 a naught t squared. I apologize. Then you get the total, so x of t must be less than or equal to the sum of these two displacements. And of course they're both 1/2 a naught t squared, or 1/8 a naught t squared. So that's 1/4 a naught t squared. And so the maximum distance you can cover in a time t is 1/4 a naught t squared. And this does indeed correspond exactly to the situation where you accelerate as fast as so equality achieved when accelerate as fast as possible first, in 0 to t over 2, and then decelerate as fast as possible in t over 2 to t. And so this actually completes the proof that this solution is indeed optimal. All right, I hope that was helpful, and thank you for watching.